you can unmute yourself. Please check it out that. Once again, I'm going to give an instruction. Please don't turn on your video and unmute your mic until you have an interaction with the resource person. Now I request Hamsaleka HN, Assistant Professor, Department of ECE, to give the biodata, read out the biodata of the today's first resource person, Srinath, Dr. Srinath G, Technical Specialist, Continental Automotive. Now over to Apsarleka. Please read out the biodata of SETS.
A warm welcome to all. Dr. G. Srinath sir received the BTech degree in electronics engineering from Jawaharlal Nehru Technological University, Anandpur in 2013. MTech degree in Digital Communication from ABV, Indian Institute of Information Technology and Management, Gwalior in 2016. PhD degree in Electronics and Communication Engineering from NITK Surathkal, Mangaluru in 2023. From 2018 to 2019, he was a visiting PhD student with the Estimation, Tracking and Fusion Research Laboratory, McMaster University, Hamilton, Canada. He is currently working as a technical specialist with ATAL, Continental Autonomous Mobility Private Limited, Bengaluru. His research interests include cognitive radio, radar signal processing, target tracking, integrated sensing and communication, and simultaneous localization and mapping. Welcome you, sir. Over to you, sir.
Yeah, hi, Hamsaleka. Thanks for the brief intro. Hello, hi, participant, all organizers. Thanks for giving opportunity to be a resource person for today's session. Maybe, I will quickly share my screen, or shall I start the session, or we'll wait for a couple of more minutes? Hello.
You can start.
Hello. Shall I start and
Yes,
present?
sir.
Or
you can start, sir. You can start.
Okay. I'll just share my screen. Please confirm whether my screen is visible or not. Yeah, is it visible?
Yes, sir. We can. The slides are visible.
Okay. Thanks for the confirmation.
Okay, sir. Okay, thank you.
Okay, I will go. Yeah, today's topic is about some special case or the case study from the automotive perspective called the localization. Towards this topic, what we specifically be looking at it is a high level overview. What exactly localization, and why do we need localization, and what are the types of localization, and then is this, yeah, and how do we do localization in the current automotive scenario, or in the currently, at least I won't give the real-time application, but with the simulated data we will see how the localization works and what is the technique behind this localization. And as I said, the one of the way to do the localization particle filter, that also we will see. And in the end we can have this some coding session where I will show with the basic simulated inputs how this localization is working, or that coding session will be there. So that's all for today. Let me start. What is localization? Basically, localization means it's knowing about the position and the orientation of the vehicle. So why do we need the localization? For example, if you want to go with the map assisted driving, first the vehicle has to know its own location on a global scale, right? That's the basic need. And also the other functionalities, suppose some decision making functionalities, or how the static and dynamic objects on the scene, where they present and all. If we want to know the such information, first of all we have to know where our vehicle is located on the global scale. So for that mainly the localization is needed. For that the mainly localization is needed. And if you look from the self-driving cars perspective, as I already mentioned, our car in relation to the static reference frame, whether it is a local or the global frame, with reference to that particular frame, where exactly our car or the eco vehicle is located. Local frame means we assume we are starting from some particular location, considering that as a 0,0 pose. From that, how far our car is or the vehicle is. From the global perspective, just like how the GPS tells, right, on what lat long or based on the WGS 98 coordinate standards, where is our ego vehicle is located. And also by knowing our own position or this self-driving car position in relation to it, where the static objects are located and where the dynamic objects are located, and this information will be coming from the sensor. But if you want the map assisted driving, we will project that sensor things to the global scale and we will see the complete perception overview. But for all these things, the localization is very much needed, and it is needed on a precise scale. Precise scale meaning that it requires like a centimeter level accuracy. Again, why do we need? Since we are working towards the completely autonomous driving, there are the certain levels, right? L0 to L5. The L0 is the lowest, and L5 is the completely self-driving. Everything hands off, legs off, mind off, everything off. And if you want to do that, we need like a precise localization so that all the static things, all the dynamic objects on the scene, we can represent them.
Not first, within
Sorry,
2-3 days.
sorry, any questions?
No problem, sir.
Hello.
Okay, sir, you can continue.
Yeah, so for all these things, precise estimation of the ego pose is very much required. Yeah. Having said that, we will look at what are the types of localization that are, that are categorized, or we can look at it. The one is, as I said, the global localization. Global localization means estimation of the ego vehicle pose on a global scale, or the WGS 98 coordinate system frame, position relative to Earth, on what lat or what long or at what altitude or what heading our ego vehicle is. For this one, we already have some sources which will directly tell us. Suppose if you install the GPS on the vehicle, since I'm just giving the example from the um, autonomous system perspective, even the mobiles also have the GPS, right? It also tells the location roughly where we are, right? So what are the sources? This global GNSS are the sources. For each and every country, they have their own names, which uses satellites constellation to tell where roughly are. So again, if you want like a more precise way, so these are the real-time kinematics, which uses the high reference base station to correct the poses that is given by the satellites. I mean, still generally for the automotive system, generally these GNSS correction based systems are highly it is not so cost friendly. So generally we use the normal GPS on the either in the mobiles or also in the autonomous vehicles. Since the accuracy of this GNSS is in terms of the meters, so that we cannot completely rely on a single system called the GNSS. So localization means it's all about estimating where the ego vehicle is there, right? If some sensor or some source is directly telling that, and why do we need other things? Like, going ahead, we will see like what are the techniques that are there for the precise level localization and all. So this single source alone, whatever the estimation accuracy that we want to achieve is a kind of centimeter level, right? That cannot be achievable with this single sensor alone, because the GNSS accuracy is in terms of the meters. Sometimes if it is urban or the tunnels, where the accuracy can go even very bad. Yeah. So but well, comes to the type, it's this is the global level localization, and there are the sensors which are contributing to it. Yeah. The other type is absolute local localization, meaning that something, some landmark or the some lane or some traffic sign on a global scale, with reference to that, where exactly the ego vehicle is. So this kind of localization generally we do on a given map where exactly we are. Earlier, that is another sensor which is contributing the information where the ego vehicle is. This is the another way of estimating where the ego vehicle is. Suppose you have the map of the road or the environment that you are traveling, meaning that each and every position of the landmark or the traffic signs or the lanes which are present on the map, you know the global position of it. And from the sensor also you will be seeing, so for example, this is some lane, some lane. You know the global coordinates of it. For example, if your ego is here, from the sensors also you will see maybe the 10 meters away some line is there, like that. If you do lane level localization, so you can also estimate your ego vehicle pose with reference to this global information that is available. And there are the different methods, like suppose if you are working with the point cloud, and if you have the point cloud map available, for example, now whatever the landmarks and lanes, i'm I'm talking about the semantic map. Semantic map means all the information is extracted in the form of lanes and the traffic signs. You know the positions of the directly. The other map is the point cloud map. Point cloud map meaning that maybe we can see in the here. Yeah, so this is the point cloud map where each and everything represented with a points which is generated before the hand, and that is available with you. Once you have that, and there are the sensors, for example radar and the lidars, which will give you the point cloud information of the scene. If you have the point cloud map, you can directly map the uh, this whatever with the point cloud sensor information on top of the point cloud map, and you can estimate where the ego vehicle is. If you have the semantic map, from each and every sensor you can extract that semantic information. For example, from the camera you can extract where the object is and all. Even from the sensors also, if you have the semantic map, extract the semantic information from the sensors and try to match with the semantic map. And if you have the point cloud map, you can use the point cloud data which is coming from the sensor and map it and try to estimate the vehicle pose. For the point cloud map, mainly the sensors are the radars and the lidars, where you get direct point cloud, right? So that you can map those point cloud onto the point cloud map. And there are certain techniques for that. I'm just mentioning what are the algorithms. For example, normal distribution transform, NDT mapping, or the iterative closest point mapping. These are all the mapping techniques to map the sensor point cloud to the point cloud map. Yeah, that's just some example I'm giving. And there are the sensors available, and which is giving you the information about the scene that you can match and estimate. The other one is relative localization, relative local localization, other type of localization. Here what it tells is, now we don't have any global information available with us, but let's assume wherever we are starting, we assume that is a reference scale or the reference point. Let's assume it's 0, 0. Starting from there, how far we are and how accurate it is completely relative from the whatever be the pose or the initial pose that we assume starting from the origin. How far we are, it is completely local level localization. So mainly this kind of localization is done using the simple dead reckoning approach. Dead reckoning approach means we have the IMU sensors, wheel encoders, which will measure the at what speed we are traveling. So using that information, we can estimate we can predict where our guess is for the next cycle, right? For example, if you are at 0, 0, if you are traveling for 1 meter per second, after 1 second, we will be at 1 comma at 1 meter position, 1 comma 1 position, let's say. So relative localization is basically we don't have any global scale information. With the considering some point or the initial point as a reference, generally it will be 0, 0, generally we assume, and from there how far it is we try to estimate. So even we can use other sensors information also, not only the odometry. For example, if you have the radar data or the LiDAR data or the camera data, we have at one particular time, we have seen some scene, we traveled for some time, and we have another, I mean, we will be seeing some another scene. So these two, there is a overlap between the scene 1 and the scene 2. We try to match these two and try to estimate the where the ego vehicle pose is. So the relative localization, the contributing sensors are not only the IMU or the wheel encoders, and combinedly we generally call the odometry. Not only the odometry, the other sensors also, even the camera or the LiDAR or the radar. If we do the frame to frame matching, earlier, if you have the global map available, that point cloud will try to match the global map. But in a relative, what do we do? At a one particular time frame, we have some frame data or the point cloud. For example, if it is sensor is a radar, you will be having the point cloud data. Once you move to the next frame, again, we will get the point cloud data. So we try to match the frame 1 and frame 2 for what position of the vehicle these two matches. So that's how we estimate. So generally, all the techniques are categorized in this way. But while comes to the real-time application, since we want the map assisted driving, generally we do global localization with a mix of all these three. For example, this technique is directly, these sensors will directly contribute you the position of the ego vehicle if you mount the GNSS sensors. But here, given the map, that map is on a global scale. Given that, from the sensor, you can see the same features and try to match. That way, indirectly, we can estimate our ego vehicle position again globally. But whatever be this relative informations, right? For example, if you do initialization instead of origin, if you do the initialization with a global scale, for example, instead of 00, you know the correct location at that particular time, you can use that information to initialize. For example, at this particular location, you know the GPS. Let's assume that is accurate, and we use that for the initialization. From there on, also, you can rely on this relative local localization for a certain duration. Once you get the global update, you try to use it, and if any deviations are there, we try to correct it. So on an overall note, on the real time, we'll club all these approaches. If you have the semantic maps, we try to use it. And if you have the odometry sensors, which will give you the relative information, or from the individual sensors also, if it is giving the relative information, we club all these three techniques and try to come out with a robust solution, which will be all the time more reliable and the more precise solution. So now we understood what is localization and what are the types and why do we need all these things. Now comes to the how do we do it. So how do we do it means we will use some estimation theory techniques. Generally, we call it as a filtering techniques. So what do we do here? Yeah, if any questions are there, maybe you can just unmute yourself and ask, because for me, I have to go back to the Zoom screen and check if anyone is raising the hand or not. Yeah, if any questions are there, feel free to, unmute yourself and then ask. Yeah, I try to address to my best. Yeah. Okay. Having said that, now how do we do localization? As I said, no, we will try to use the estimation theory techniques or the filtering techniques. So what exactly we do? Now let's take a simple example. We ourselves, or I myself, want to estimate my position. If I have some information, how do I do that? We'll just discuss about that. For example, I am at 00 and I know how I walk. For example, my foot length is like 12 inches, 1 feet. for each and every second I take 2 steps, let's assume. So 2 steps means I can cover 2 feet. So if I am initializing my pose at 0, 0, after 1 second, my foot length is 1 feet and I take two steps. So I will be at a 2 feet distance after 1 second. That's how we generally do it, right? So even the mathematically also we do the same way. Whatever the information or whatever be the mathematical model. For example, now I said I take the 2 steps or the my feet length is some mathematics or some number behind it, right? Suppose if you have some mathematical model how you proceed or how you move, using that we can predict or where I will be after some time. So in a filtering techniques, we call that as a motion model or the process model. So I have some mathematical model given the inputs or the taking some inputs, how at what speed or at what angle or what air rate I will travel or the vehicle will travel. Using that information, if you have some mathematical model, you can roughly guess where you will be. Okay. Now let's assume, let's come back to the example what I took, like, after 1 second I will be at 2 feet away, right? Like that, if I keep on calculating without realizing that whether I stop or based on some surface I skid, without realizing based on some obstacle I just stop. Without realizing that, I simply keep on calculating for each and every second, 2 feet away will be like that. If I keep on calculating, I'll be drift away. For example, some obstacle came, I actually stopped. But according to the mathematical model, I didn't stop calculating. I keep on calculating. So after some time, what happens? We will be drifting away from the where we are actually. So using the process or the motion model alone will after some time we keeps on drift because we don't have, sorry. Okay. Yeah. We drift away. So next step is if you have the other source of information which will correct. So then we can make use of that information. We can correct that drift, right? So that is measurement or the observation model. From some sensor, let's assume I recruited a GPS guy who is sitting on the first floor and he is just watching me how I walk on the road. And based on this mathematical model, I'm keep on calculating, and the GPS guy or whoever I recruit, maybe the GPS guy or the camera guy or the radar guy or the lidar guy, whoever we place on the vehicle, uh, they will be watching, right, where exactly we are. We will make use of that information to correct. My prediction, for example, this mathematical model, after maybe 3 minutes, I'll be at 6 feet distance away from where I initialized. But there is a GPS guy who has observed me and told me that you didn't travel for 6 feet actually. There was some obstacle. You just stopped for few seconds and you didn't take one more step. You are actually at five steps away. So there is another guy who's telling that information. You have to make use of that information and the correct. So that is what happens in the filtering cycle. There are the 2 steps. One is the prediction step and the other one is the update step. In the prediction, whatever be the models that you have, consuming how your ego vehicle, considering the ego vehicle kinematic information, for example, all the angular and the translational velocity, we will make use of it. And based on some mathematical model, we will predict where the ego vehicle will be. And next step is the update step. We will correct from the measurements. This measurements can be this GPS sensor, or if you have the map of the environment, whether it is a semantic map or the point cloud map. If you have the semantic map, from the sensors also, radar, camera, or the lidar, we try to extract that semantic information. Semantic information meaning it only consists of this lanes and the landmarks, traffic signs, only such information. Such information we will extract from the sensors also. We will try to map or the match on top of the map that is available with us, and we try to use that information to correct. As I said, the whole filtering technique, it consists of only two steps. One is the prediction step and the measurement steps. So as I said, for the prediction, we will try to make use of ego kinematics. Ego kinematics means whatever the ego vehicle, how, at what speed, on what angular rates it is traveling. We call that as a velocity in all three directions, Vx, Vy, Vz, and the roll, pitch, yaw rate. All these six information we will use, and we have some mathematical models, for example, constant velocity or the constant acceleration. If you don't have any turn, then these two models will work well. If you have the turns, I mean the vehicle is taking turn, then coordinated turn rate vehicle model or the constant turn rate acceleration model. There are some mathematical models based on the use case. For example, for the ego vehicle, it consists of both straight roads, turns, and everything. So it's using the mix of these things will give you the better results or the better prediction results. So based on the application, the availability, there are from the available mathematical models, we'll pick the best suit one based on the application. Similarly, the measurements also, measurement sources, you have the lot of sensors, right? The GNSS or the odometry or the radar, LiDAR, these are all sensors which will be mounted on the ego vehicle for the self-driving purpose. Whatever the information that comes from the sensors, whether it is which gives local values and then global values, and then whatever the semantic map or the point cloud map available, we try to make use of all this information, we try to correct. So now the question comes, you have the prediction model and the measurement model, which one to trust more? So we have no idea, right? For example, if, as I said, no, I know how I walk, right? So I can strongly tell my mathematical model is very good, I have to trust more this only. Why should I trust the GPS guy who is 1 floor away, who is watching me? So there is a like a contradiction or the some fights between these two prediction models and the prediction and the measurement or the predict or the updates. There is a contradiction or the fight between these two, which one to trust more. So which one to trust more, or we need some mathematical model or some principle to give a weightage between these two, right? So that is what this Bayes principle tell. So which one we have to use more? This Bayes theorem we might have studied during our schooling days way back, but that time even I myself don't know that. This simple Bayes principle equation is ruling the whole target tracking theory or the whole estimation theory. This is the simple equation which is governing whole estimation theory. I was not knowing that. Otherwise, I could have studied more about this equation during that time only. But the later coming, I mean, while looking at the estimation theory, so this is the simple equation which is governing whole estimation theory. So what it tells, you have whatever you want to estimate something given something. So if you want to put in a words, for example, using some mathematical model, you have some prediction or the prayer you have. So for example, in my case, as I said, no, after 1 second, I will be at 1 or 2 feet away. The 2 feet away is the prayer. There is a GPS guy who is also giving the information, right? So that is the likelihood or the, I have to use that information. I have to use that that measurement information, and how likely my prediction is. I have to club and bring out the posterior information. So this, based on this principle, we try to accommodate whatever be the prediction on the, I mean, based on the motion model, whatever the predicted value, and based on the measurement, we will be calculating the how likely that prediction is. By multiplying, you will get a posterior estimate, which will be a corrected one or the weighted one given these two information, prior and the likelihood. and also it makes use of this uncertainties. For example, this mathematical models, there are the tunable parameters, how good they are. So those will be represented in this noises. There is a each and every model, these are for the given model and the given application. These are the tunable parameters. This q is process noise. How good your mathematical model is very good, then this value will be very, very low. I mean, variance will be very, very low, will be giving. And if your measurement is highly trustworthy, this measurement noise R will be very, very low. So based on these uncertainties, we call variances are nothing but uncertainties. If variance is very big, the uncertainty around is very high. If the variance is very, very small, then the uncertainty around it is very, very small. So how you can interpret means, in the mobiles we will be seeing the GPS, right? There is a very, very thick blue dot available. Around to it there is a very big circle, sometimes it comes, right? So that big circle is the uncertainty or the covariances associated to that blue dot. The thick blue dot is nothing but the position, and there is a big blue circle whatever we see on a Google map. Some if you keep zooming, if you know, if you just open the Google Maps and if you look at your location, there is a very thick dot, and around to it there is a circle. The thick dot is nothing but the position, and that circle is nothing but the covariance or the uncertainty associated with that thick blue dot. If that circle is very, very small, so GPS is more accurate. Like that you can interpret. Yeah. So given those uncertainties or the covariances associated to motion model and the measurement model, and using the base principle, we try to update and try to get the better estimate by using the sprayer and the likelihood from the sensor measurement. Yeah. And all the estimation theory or all the filters uses this simple principle, and there are the number of filtering algorithms that are available, mainly categorized into two types. One is the linear filters and the other one is the non-linear filters. And what is the difference between the linear and the non-linear filter means, suppose this motion models and the measurement models are the linear. A linear means y is equals to mx. Let's say x is input and the y is the output, and there is a linear relationship between these two. So in here, what is x means your previous value, and what is y means your current value, and there is a mapping between these two. If that relationship is linear, then the linear algorithms will give you the good results. And if this relationship from the previous x of k minus 1 means it's a previous value and x of k is the current value, whatever be the mapping function that is there, right, fk, if that is a non-linear, then the non-linear algorithms will do the better job. Similarly here also, for the measurement also, wherever the mapping function h is, if that is linear, for example this motion model and the measurement model both are linear, the linear algorithms will do the good job. And if it is a non-linear, then the non-linear algorithms will do the good job. So this under the linear algorithms we have the Kalman filter. Under the non-linear algorithms we have the extended Kalman filter, uncentered Kalman filter, cubature Kalman filter, particle filter, or the algorithms that are available. As I said, Kalman filter means whenever this motion model or the measurement model both are linear, and the Kalman filter is the good candidate to work. But in reality, this linearity won't hold for the majority of the applications. So then using the linear filter for such applications will leads to the won't give the fruitful results. So, and then while comes to the non-linear algorithms, as I said, no, extended Kalman filter, that is the one of the first algorithms that we see any filtering techniques. In the extended Kalman filter, what it do is it try to linearize this mapping function. For example, if it is a y is equal to mx function and that is linear, so linear algorithm will work. And if it is a y is equals to m into x square, then it is a non-linear, right? So the linear algorithms won't work. This extended Kalman filter, what is the idea behind is, you try to linearize this mapping. If you have y is equals to mx square, you try to differentiate one time, then y is equals to 2mx it becomes, right? So now it holds the linearity principle. So you can whatever be the Kalman uses, right? So extended is basically you try to linearize the mapping functions and do whatever the earlier process that it do. But if suppose if the degree of non-linearity is very small, then no, mapping the non-linear to linear will works fine. But if the degree of non-linearity is more, then again output will drift away or the deviate from the truth. What is the degree of linearity? For example, y is equal to x square. So one time differentiation will work. If y is equals to m into x power 4, then if you do one time differentiation, still the system will be non-linear. And if you keep on doing the differentiation, sometimes whatever be the equation, right, those are not observable. Observable means differentiation won't exist, or the whatever be the matrix that you use, it becomes what do you call it, determinant becomes 0, and there will not be any the observability will be lost. So to avoid that, the other algorithms come into the picture to handle the higher degree of non-linearity. Those are the algorithms, as I said, after the extended Kalman filter. And there is an uncentered Kalman filter and the cubature Kalman filter. So what are these two algorithms? What is the basic idea behind these two is, instead of passing one point, for example, this x of k minus 1 is the point that you pass and try to map using some function, and you get some value at particular time frame. So instead of using only one value, because using one value means if it is a Gaussian case, only we will pass mean and we will map and we will get mean. So mean and covariance is good enough to represent the Gaussian. Okay. And if this f is a non-linear, even though you pass x value as a Gaussian, because of this non-linearity, the output will not be a Gaussian, right? So simply passing one value to a non-linear function and try to get it won't work. So what are this cubature and uncentered Kalman filter do? Instead of passing one point, you pick some number of samples from the Gaussian and you pass those samples through this mapping function. Whatever be the output it comes, you try to reconstruct the mean of it. So that's the basic idea behind those two filtering algorithms. Even those two algorithms also, I mean, if those whatever be the samples, if those are good enough or represented in a correct way, it will try to work for the non-linearity. But there are the cases where there is a multiple possibility of the estimate can be possible. So for such cases, those two algorithms again won't work. So then now comes to the particle filter, which is an algorithm to handle the high degree of non-linearity, but it comes with computational cost, and which is bearable for the current systems or the hardware that is available. So whatever be the current localization algorithms uses the particle filter. Even at Continental also, we use the particle filter based localization algorithms. And then why I said this, all this Bayes and all also, particle filter is also uses the Bayes principle. That's why I just touched this roots of it, so that you won't miss. And also I just mentioned what are the other algorithms in the literature that are available. and why we are using this particle filter currently, briefly touched upon, so that if I simply directly tell the particle filter views, and people will make just confused, I just give a brief of a background to it. Yeah. So now at Conti also we use the particle filter based algorithms. So not only this, now even the current research, it is way ahead. Instead of filtering algorithms, now if you look at the literature, you will find the graph-based approach. Even this learning-based approach are also there. But at least, I mean, that shift will take some time. But right now with the Conti, this particle filter-based algorithms we are using, and which is the real time. So what is this particle filter-based algorithms means? Simple, the same principle what I said for the UKF, or the, I mean, uncentered and the Kubacher-Kalman filter. Instead of passing one mean value, here, we pick some number of samples. So we call that as a guess. So whatever be the particles, right? These are the guess. For example, I myself want to estimate my pose. So I make 100 guesses of myself. For example, I am at 1,1, let's assume, and I don't know exact pose, but I generate the 100 or the 1,000 guesses of the pose. For example, at 1 means I pick 1.1, 1.0.1, like that. Some guess we pick it, and based on information which come from the sensor or based on the map available, we try to give a weightage to the each guess what we made, right? Each guess whatever we made, we'll try to give a weightage based on the measurements that we get. So in a technical sense, whatever be the picking the guesses right, we call this as sequential importance sampling. So for whatever be the known distribution, simple Gaussian or the uniform, based on the information that is available with you, we pick some guess. For example, some 500 guesses I pick from the Gaussian PDF. If I know roughly that I am at 1 meter with some uncertainty of 0.5 meter. So by passing this mean value of 1 and the 0.5 meter as a deviation, I pick some 100 samples. So this 100 values we'll get. Among those 100 values, we have to pick the correct one. Okay. To pick the correct one, we use the measurement information. For example, if you have the simple GNSS sensors, and let's assume it is decent enough and accurate, it is giving some value. So the GNSS gave you are at 1.2. So whatever be the other values, right, apart from the 1.2, based on the GNSS uncertainty, we try to give a weightage to the particles or the guesses. So whatever be the guess you made, we will pass through this prediction function. Once you receive the on the measurements, you will try to update and you will get the posterior estimate of it. So that is what here it same principle. We try to you pick the guesses of it, you predict, and once the measurement comes from the sensor, you give a weightage and try to calculate the overall estimate of it, or the best position of the eco vehicle. The same if you want to spread this equation into same base principle. So if you have the k minus 1 if you have the at k minus 1, you have the ith guess, you try to predict using motion model. Once you have this prediction or the prayer from the measurement and from the sensor, you got some measurement shed. From the GPS, you got some position. So you have to you have to find out how probable or how likely whatever be the prediction that you made. You have predicted xki, right? That xki, how likely it is given the zk measurement. So this is the prior or the predict. and this is the update from the measurement, or the how likely your prediction is given this measurement. So based on that, we try to give a weightage, and while giving the weightage, we also consider the previous weightage of it. Instead of instantaneous, how was this guess on a previous instance, we also consider that. That's why this WK minus 1i is also there. And on a overall, this current weightage of the particle is decided, or the how good the guess, how good that ith guess is in terms of weights, we try to calculate. Yeah. If you look at the block diagram, as I said, all the filtering algorithms will have the predict and update. Even the particle filter is having the predict and update steps. And we have the initialization. Initialization means if you are working on the local scale, as I said in the starting, there are the types of algorithms, right? On a local and the global. If you don't have the global information, you just initialize with some 0 reference, and you keep on predicting and updating, predict using motion models, update using sensor measurement, and try to estimate. And then this resampling steps, I will talk about it. Yeah, same thing. You have some guesses over the particles, we call it in a technical terms. And if you have it, using the predict step, you try to propagate using motion models. And once the measurement comes, you try to give a weightage to the each and every guess that you made, and you update the weights. Once you have the weights and the guesses, whatever you made, suppose for the 5 guess, for example, there are the total 10 guesses what I have made. Among the 10, once the measurement comes, the 2 guesses has a more weightage. So based on the weightage, we will multiply, and then we will try to get the estimate. So there is a one way, right? Whichever be the guess which is having the higher weight, that itself I can consider as an estimate. So there is a one way to calculate the overall estimate. Instead of that, instead of simply picking the highest weightage particle and neglecting all the guesses, we try to use all the information. That means we'll try to multiply the all weights with all the guess, so that I will not be losing any information or neglecting any information which is available. Always, if you have the information, instead of neglecting, we try to use it in a better way, so that we will get better estimate. So this is the another way. So instead of the one way is whichever way the particle or the guess which is having the max weight, that itself we can consider as estimate. The other way is you try to multiply the based on the weights and all the guess, and you do addition. That also will give you the estimate. So this way is the better and stable. So generally this way people use it. So now this resampling step, right? So whatever be the 100 or the 200 guess that we made, after the measurement comes, among the 100 or the 200, based on these weights, I came to know that even though I make 100 guesses, there are only the 10 guess which are highly contributing or the highly likely given the measurement. So there are rest 80 or the 90 or the waste, I mean, which is not actually contributing. So then what is the point in carrying those non-contributing guesses to the next step? It is of no use, right? Instead of that, the one way is you just neglect. Suppose at first step, I pick the 100 guess. Among that, once the measurement comes, I identified that only 10 guesses are useful. So for the next step, I just eliminate all the 90. I can only go ahead with the 10. Okay, that is the one way to resample or uh, do the propagation. So if you do that way, so what is the problem? What is the problem is, for example, at the next step among the 10, so for the first step 100, from the 100, we identified the 10 are good. The rest 90 we have neglected. At the second step, among the 10 available, only 5 we identified are the good candidates. So while comes to the third step, only 5 are available. Among the 5, let's say only 2 are the good candidates. So at that step, we neglect other 3. While comes to the fourth step, you have only the 2 guess. So the 2 guess are there. Let's say from the measurements, we realized that whatever be the 2 guesses that you are available, right? Those are not at all useful. So then what happens? We left with nothing. There are the no guesses which are available, which is matching with the measurement, right? So that way, I mean, that way means the neglecting the whichever be the bad guesses is a bad move, because after some time we left with the 0 guess which are contributing or the aligning with the measurements. So instead of that, we have to do the resampling in a better way. Somehow we have to cut down the non-contributing guesses, but still at each and every step, we have to maintain that some guesses should match. So whatever be the problem that I said, right? If we keep on eliminating, after some time we end with nothing. In the particle filter sense, we call that as a particle degeneracy problem. Particle degeneracy means whichever be the guess that you made, or whichever be the particle or the value which is not at all contributing, we realize after some time we end with there is no guess and the filter will diverge because there's nothing is there to contribute. So to eliminate that, there are the different techniques in the resampling, how to do it in a better way. So what the general idea is, suppose for example on the first step 100, no, we identified that 10 are good guess, right? Instead of eliminating 90, so we refill the rest 90 with this 10 best guesses. Okay, so that at every time we have the 100 particles only, but instead of eliminating whatever be the other 90 which are not at all useful, those 90 will be filled by useful guesses. So that way we do. So in the literature, for the resampling, there are the lot of techniques that are available. Maybe the 1 or 2 I will touch. So this resample, right? We will check among the available particles or the gases, how many are they effectively contributing. If those effectively contributing are the very, very less, or the less than whatever be the threshold that we set, then we do the resampling or the refill the guesses with the correct ones. So that's what this resampling step will do. So we initialize, if you have the global information, we initialize with it. If you have the local information, we just considers that. And based on the motion models available, we'll try to predict. And based on the sensor measurements which are available, we try to update or they correct the predicted guess. On a overall, we try to estimate where exactly our eco vehicle poses. So on the one more step, if whatever be the guesses that we made, which are not at all contributing, then we try to do the resampling or the refill the bad guess with good ones. That's what. This is the one cycle of the particle filter algorithm. As I said, for resampling, there are the lot of techniques which are available in the literature. I just touch upon 1 or 2 techniques. The one is the multinomial technique. So here, what do we do is, for example, the 100 particles or the whatever we have, and for each and every particle you have the weights, right? So using the weight, I create a cumulative weight circle. For example, for the first particle, the weight is 1. For the next particle, the weight is 3. So I try to add and create this weight circle, just like I think the roulette everyone knows, right? Where we just press that button and wherever the arrow stops, we pick that particular value, right? In the same way, this multinomial will work in the same way. Instead of the letters or the symbols that we see in the roulette circle, here we will represent that with the cumulated weights. Cumulated weight means, for example, this is the first particle which is having the weight of 1. This is the second particle which is having the weight of 2. But here an cumulative, if you want to represent, here it will be 1 and it will be 3. If the next particle weight is 1, So then 1, 2 plus 1, it will be 4. So instead of the numbers, this represents the weight circle, and whatever be the roulette or the push button will be there, right? That push button, if you press wherever this arrow stops, you pick that particles. So if I want to explain in a from the probability sense, for example, if I have the 3 particles, so each one is having the weightage like this. For example, P3 has a more weightage. For example, P1 and P2 are equally likely, but it is less weightage than the P3. So instead of carrying this P1 and P2 or P3 directly, since the P3 is a more useful guess, so I can pick that one twice, or replace the bad ones with the best ones. Among these two, I can just replace any one with this, so that my guesses will be like, good weight ones I can carry to the next cycle. This is the idea. And also, if you want to explain on a coin sense, suppose I have the head and tail. So both are, suppose this algorithm or this method has some disadvantage. That is, suppose if you have the 2 particles or the 2 guess which are equally likely, and there is a chance that if you play this method, you end up with only one outcome. So just to explain that, if you have the coin, right, you have one head on one side and the tail on the other side. So if you play a toss for 2 times, there is a chance that sometimes both the heads can come or both the tails can come. But while looking at the input, both the head and the tail are both are equally likely. So at the output also, or the output of the resampling step also, both should be representable. But with this method, there is a chance that even though at the input side, the guess or the particles are the equal likely, if you use this method, there is a chance that we end up with, or we eliminate the one of the good guess, or the variance at the output is sometimes it become high. So that is the one of the drawback of this method. So to overcome this, there is another method called the stochastic universal sampling, or the low variance sampling. So in this method, what do they do? Instead of picking one arrow, they fix, they already have the n arrow circle. For example, if n particles, then n arrows, n guess, or the n particles, then n arrows. You press one time. So each and every arrow where it stands, only one time we'll press and pick all the n resampling particles at once, so that we don't lose the equally likely guess. For example, with this method only, you have placed head and tail here, and if you have the 2 arrows, right, then all the time the output will be head and tail only. There is no chance that 2 heads or the 2 tails will come. So that way, even though the input is equally likely, at the output also we try to maintain, output means at the resampling output also we try to maintain those guesses, or the variance from the input to output in terms of the equally likely particles, or in terms of the equally likely guess, is low with this methods. That's why they call this as a low variance sampling method. This is one of the method that currently used in the literature. Yeah. So this is a basic idea of the particle filter based localization, or the on a general filter based localization. For each and any filter, we will be having the predict and update step. Predict from the using the motion models, update from the measurements. If it is a particle filter, to handle the non-linearities, we are moving it. And in the particle filter, basic idea is we make the guess of what we want to estimate. We call each guess as a particle. For each and every guess, we predict, and once the measurement comes, we will try to give a weightage for each and every guess based on the weights what we receive, and we multiply with the guess, so that we can estimate things correctly. So that's what we do. So any idea, any doubts or any questions here regarding this particle filter based localization? Whatever the theoretical session I have come out, I mean, it's finished. Maybe like if you don't have any questions or the doubts, we can just jump to the simple particle filter localization example from the with the coding script. I have some MATLAB script which will do the particle filter based localization only, but it uses only the GPS sensor as the input. So I can just show that how the results are, and whatever I'm talking, right, whatever be the prediction step and the update step that we are talking about, where exactly those are happening, whatever be the resample I said, where those things are happening, that and all we can have a look. So that for the simple case study of localization, whatever be the theory that I have presented, it has some visual sense, so that it looks good, or it can be more explainable in a better way. Yeah. Any questions? In the chat, I see. I see one question from the Jeevit, which is best for the object tracking among Kalman or the particle filters. Yeah, that best, as I said, based on the models that you have. Suppose whatever be the motion model and the measurement model, if both are linear, then the Kalman is the best one. So if those two are not the linear, I mean, if we look at the literature, if the prediction and the whatever with the motion models and the measurement model, both are linear and the additive Gaussian, Kalman filter is the best. No other filter can give the better output than this. But if those two are not in linear, I mean, there is a non-linearity associated with it, and definitely the other filters, non-linear filters, we have to look at it. Among the available non-linear filters, particle filter is the best candidate, uh, which can handle the multi-hypothesis estimate. Yeah. Okay, if there are no questions, I may just jump to the some simple MATLAB script which is available with me. Is it okay?
Anybody is having any queries, any questions, you may ask to sir. Any questions, participants? Any doubts? If you have any doubts, please unmute your mic and turn on the video and you can ask sir. Ask Srina sir, please. Any participants having any doubts?
No, madam, thank you.
Okay. I will just share my screen so that we can have a look at some simple MATLAB script which is available
sir,
with me. Okay.
Okay,
Which is about. Okay. Okay. Is my screen is visible?
Yes, sir. It's visible, sir. It's visible, sir.
Yeah. So this is a simple program which uses the GPS sensor data. The only one sensor which is available with us. Let's assume the GPS. So, and this is not the lat long level data, since it is simulated. All the things is based on the simulation. It is not based on the real lat longs available and all. The data is also simulated on a local scale, and if you have the GPS data and if you have some motion model, and if we have some ego kinematics with which ego is traveling. So how do we do this particle filter based localization? Yeah. So I'll just maybe run so that we can see the final output, and then we can just discuss. So if my is the output screen also visible, or the only MATLAB script? So from the MATLAB script, there is a figure pop up that is also visible, or no? Hello, can someone confirm?
It is visible, sir.
Okay. So if you look at here, I have just generated some sample data. So there is a blue line here, and there is a red line, and there is a black line. Okay. This blue line is the ground truth, where exactly the ego is traveling. The red line is a kind of estimated ones with the noisy GPS measurement. So this green dots which are available here, right? Those are the noisy GPS measurement. So given this much noisy GPS measurement, we are trying to estimate where the vehicle is. And this black line is if we use the only odometry based, only use the IMU information, over a time, if you won't correct, this will be drift. Whatever I'm talking about, the drift, right? This black line, if you see, if you don't update, this drift will be keep on happening. So in one run, it looks close, but on a multiple runs, if it may go even worse. And this black dots are there, right? Those are the particles or the gases at each and every time frame. And there is a circle or the ellipse around to this black dots, right? That is the uncertainty or the variance associated with the estimate. Whatever the example given, right, with the GPS in the mobile, there is a thick dot and there is a very big circle, right? So that is that circle I'm just representing for the visual sense. Okay, so given the GPS measurement, we are trying to estimate the pose of our ego vehicle, and it is aligning with the ground truth. Okay, so it may look shaky because there is the GPS measurement, the green dots which are available, right? It is so noisy. Suppose if you want to estimate the output, if you want the centimeter level accuracy, so from the inputs also, some of the input should contribute such level of information. Then only the output will be reflected in that way. So since here the GPS or the too noisy, that's why this no, the shaky curve is observed. Otherwise, the output, if there are the other sensors, suppose map is available, and from the sensor also data is available, and which is having the centimeter level accuracy, then we try to achieve such level of output. So over a time, it keeps on estimating, predicting and updating, predicting and updating. So even this circle or the dots, you can see whenever predict happens, spread will be more. Whenever the update happens, this collapse and it will be, circle will be less. Yeah. Okay. So what's happening here is I will just quickly touch upon, not on the animation things, only for one cycle in the PPT, whatever I have shown, right? The predict and update cycle, what is happening, we can have a look at it. Okay. See, there are the particles or the guess that we make for our pose, and there is a weight associated for it. So in the initialization, so I already initialized with all my guesses with some, if you look at the initialization part here, this is a particle I have just initialized with zeros because I assume I don't have any global information. The GPS is there, but GPS is also giving some relative information. Since it is a simulation, I just assumed that way. That's why I just generated the particles around it and its weightage, since that is the first step and I don't know which guess is equally likely. So I don't have any weightage, particular weightage. That's why I gave the uniform weightage. So uniform distribution is the best representation to give a equally likely information. Suppose from this scale to some low to high, this is the scale available within this scale, and I don't have very preference. So then the uniform distribution is the better candidate to represent, and based on that, we have given the weightage. So at the initialization step, given such initialized particles and such weights, so now we have to predict. So pick the one particle. So there is a loop running for the whatever the 100 guesses that we are making. So pick the each and every guess and each and every weight of it. This is at the previous frame. And now you predict with your motion model. So the motion models, so I said, right, there are the different motion models here, I guess. CTRV model is used. CTRV means coordinated turn rate velocity. Whenever there is a turn, I'm just checking the threshold. Whenever the turn value, right? If it is more, it will switch back to the other models. There are the two models available here. One is simple constant velocity. Constant velocity means whatever be the previous pose plus velocity times the previous value. Okay, that model, or if you have the angular return also, use such mathematics and try to get the output. Okay, so where is this? Okay, so there is you pick one guess and you have the previous weightage. That guess you predict using the motion model based on whatever be the model that you assume. Since if you look at the figure, here there is a turn, right? So I just in this function there are the two models. One is the CV and CTRV. Maybe based on the turn value, it pick that particular model and give the predicted guess. And there is a measurement Z is coming. That is the GPS guy. Whatever be the green dots are there, right? The green dots are also coming, and there are some parameters associated with it here. If you look at here, I picked the number of particles or the guess as 100, and simulation time I'm representing as a 50. And for each and every 0.1 second, there is a measurement coming. That's the assumption. So for each and every 0.5 second, one green GPS dot is coming. That is the measurement. I have to make use of that information and correct my predicted guess. This is the predicted guess. And for a simple thing, since GPS also directly give me the position, and my predicted guess also put the position for the thing that I want to estimate. So I can just simply take the differentiation, and whatever be the difference, if the difference is more, and considering the uncertainty, R means what is the uncertainty of the GPS measurement. So if you look at it, we will be just giving the weightage based on its uncertainty. Okay, so once, suppose if I don't have uncertainty, simply this difference can work. Since I have the uncertainty, that's why I'm giving the likelihood kind of weighting. So once you calculated the weighting based on the difference, and you have your prior also, as I said in the PPT, we will multiply with the prior weights also, just for the stable things over a frame, how the things works, right? So current weightage we have calculated, and it is multiplied by the current weightage. Means this current weightage is calculated from the given prior and the measurement. So you have the prior, you have the measurement, and you are checking given these two how likely. So that likelihood is being calculated here and the converted in the form of weightage, and that weightage is being multiplied with your previous weightage. So that way you are calculating the weight at this particular instance. Now you have for this particular particle, and this is the new weight calculated. Okay, like that for whatever be the number of particles that are available, you predict using the motion model and you correct using the whatever be the measurement. In this simulation example case, GPS, you try to correct it. And once you have the weightage, you just normalize it so that it looks like PDF value. It won't go beyond 1, and total value will also be 0 to 1. So once you have the weights and the particles, so you will estimate just by multiplying the particles with its corresponding weights. And I'm also calculating the variance associated with it. How we can calculate? You have the estimate and you have the particles. So the simple formula, mean minus data, that formula we can use and we can calculate the variance. So whatever be the this circle I am plotting, that is the variance. Whatever be the black dots, that is the each and every guess what we are making. This green dot is the GPS measurement which is actively coming. So what we achieved, even though GPS measurements are noisy, by using these techniques, we were able to estimate somewhat less uncertainty position. Yeah, based on this. Yeah, and this figure also tells if you don't correct, you can drift away. For a shorter duration, you can trust the relative information. If you keep on predicting without update, you just drift. Yeah, because the mathematical models won't represent the reality. I mean, so over a time, we just drift. Yeah. Okay, and as I said, no, we will check how effective these particles are. Okay, how if that number of effective particles are less than some threshold, then we do the resampling. The resampling, I said the different steps, right? The low variance resampling or the second method, what I said. So what we do, we will create that roulette example I gave. We create a cumulative sum circle, and you directly generate the n arrows of it. Okay, you have the cumulative weight circle and the n arrow wheel, and you have to press push button one time so that n arrows will keep rotating and stop at one particular time. So just to create that push button is created here, some rand. Okay, using that rand, it will just circulate and stop at all the arrows will stop or point to some weight circle, and that each arrow we have to check in a weight circle where it has stopped. Okay, so where in each and arrow in a weight circle where it stopped, we have to fill or replace current particles with this resampled particles. Okay, so the basic idea why do we create the cumulative circle means there are the particles with less weight, means the number of arrows it can cover will be less, right? Okay, so that way during the resample, the highly weighted particles will come as output or they come as outcome of this resampling. So in that way, we get away with the low weight particles or the low weight guess, and and the particle degeneracy problem where I said, right, if we eliminate at one time, we end up with nothing, which actually represents the measurement, right? So that problem also we can eliminate this resampling methods. If you look at the literature, there are a number of techniques which are available. For the resampling techniques alone, if you keep on digging, that itself take more than a day for each and every resampling technique. Yeah, like that for each and every step, if we just gave general overview of the particle filter based localization and just gave some example or the sample program, which will just give you some outcome. Maybe I'll just run for one more time just to visually see over a time how it is estimating. Yeah, maybe that's all from my side. It will be running. If anyone has any questions, feel free to ask.
Any participants is having any question, you can ask Srinath sir. You can unmute your mic, you can ask. Any questions? Any questions? I request any participants is having any queries, any question, you can ask Srinath sir. Please do unmute your mic and you can ask. Okay, hope everybody has understood whatever the concept has been taught by Srinath sir. It's really wonderful session, sir. Hope no participants are having any doubt in this session. Anybody is having any doubts? Okay. Anyhow, thank you, sir. Thank you.
Yeah.
Behalf of Saheb family, I heartily thankful to you, Dr. Srinath sir, who is working as an technical specialist in continental automotive industry, Bangalore. Special thanks, sir. Thank you so much for accepting our invitation and come as a resource person. It's really pleasure to have you, sir. Yeah, the session is really very interesting and very informative. Thank you so much, sir.
Yeah, thanks once again for the organizers. I mean, thanks for the opportunity. Yeah, thanks.
Thank you, sir. Thank you, sir. Thank you so much.
Thank you. Bye.
Bye, sir. Bye, sir. Now we are going to have a second session. Whose the resource person is Mr. Nandi Dharma Kishore, sir, who is working as a founder and CEO at Ashtaksha Labs. Now I request Manasa MR, the Assistant Professor, Department of ECE, to read out the biodata of Nandi Kishore, sir. Mansa? Mansa, madam?
Yes, ma'am. Yes, ma'am. Am I
Yeah.
audible?
Yeah, ma'am. Yeah, ma'am.
Okay, ma'am. Okay, ma'am. So, good evening, everyone. So, I'm Mansa, working as an assistant professor in the Department of ECE, SSIT. I take this privilege to introduce our distinguished speaker for today's session, Mr. Nandi Dharma Kishore, HN, the founder and CEO of Ashtaksha Labs Private Limited, Bengaluru. He is a global leader in cybersecurity and a visionary innovator with over 2 decades of extensive experience in anti-malware research, cybersecurity, and software development. He has held key leadership roles in several globally renowned organizations. He served as Assistant Vice President at K7 Computing, Bengaluru, where he led anti-malware research and product development. He worked as Director of IoT Security Operations and Research at Subex Limited, where he established an IoT security research lab and developed strategies to protect next generation connected devices. He served as Senior Security Manager at Samsung Electronics, South Korea, managing critical security operations and contributing patented solutions for device security. Earlier, he worked as senior research scientist at McAfee Labs, Bengaluru, where his work resulted in the grant of 4 US patents in anti malware research and development. His contributions are remarkable. He holds 4 granted US patents and has 3 published patents associated with McAfee, Samsung Electronics, K7 Computing, and Astraksha Labs. He is regularly invited as a keynote speaker panelist, and chairperson at reputed global forums such as Data Security Council of India, the Association of Antivirus Asia Researchers, the Cybersecurity Summit Bengaluru, and the Confederation of Indian Industry.
Dr. Manasa, we lost you for a
PhD
couple of
scholars
seconds.
at IIT Madras and
Please proceed.
In progress.
Very sorry for the inconvenience caused, ma'am. So he also serves as member Skill Advisory Committee for Emerging Technologies, Karnataka Digital Economy Mission, Government of India. He also serves as member Research Advisory Board at Dayanand Sagar College of Engineering, Bengaluru. He also serves as member Academic Council at Global Academy of Technology, Bengaluru. Talking about his academic background, he has completed pre-PhD research at MS Ramaya Advanced Studies, Bengaluru. He holds a Master of Applied Science in Information Technology from RMIT University, Melbourne, Australia, and Bachelor of Engineering in Computer Science from VTU. On behalf of the Sahe family, I heartily welcome Mr. Nandi Dharmakishore HN Sir as the distinguished speaker for this ATAL Faculty Development Program. With his vast knowledge and expertise, we are confident that this session will provide us with valuable insights into real-time automotive systems and their security challenges. Without taking much of your time, I now warmly invite our speaker, Mr. Nandi Dharma Kishore Sir, to take over the session. Over to you, sir.
Thank you very much, Dr. Manasa. Hope my screen is visible. Am I audible?
Yes, sir, you are
Yes,
audible.
sir,
audible, visible.
Yes, sir.
All right. Thank you very much for having me on this ATAL FDP. I believe like these FDP sessions are shaping the nation in having a resilient Bharat, right? And I thank the Saheb family as well as the management, Dr. Komala and Dr.Ghouse for having me and for the invitation on this FDP. All right, so before we get started with this session, it is very important why we are focusing on cybersecurity in almost all the sectors. And the title that was given to me was Security and Privacy in Real-Time Embedded Automotive System, right? Once again, I thank Dr. Manasa for the very warm introduction about myself.
Thank you, sir. Thank you, sir.
And I know like this is a Friday night session, a weekend. I'm not going to bore you with the theoretical aspects of cybersecurity, but I'm going to keep that very minimal and focus mainly on automotive security. Right. Before that, a quick introduction about my company, Ashtaksha Labs. It is Ashta Aksha, that is 8 eyes. If you look at the logo, it has 8 dots that we are going to surveillance the digital ecosystem of Bharat from all the 8 directions. Well, that is for layman. Anyway, like in upcoming slides, we will be looking at each and every dot which is represented in this logo. And in the middle, we have a cybersecurity shield with an eagle eye. This company was incorporated in 2023 with the vision of to serve the nation, meaning we are going to surveillance the digital ecosystem of Bharat, right? And with the mission of creating or producing committed cybersecurity and AI/ML professional. And going forward, the scope will be, we will elaborate or expand the scope into embedded system security as well. Thank you very much again, like for to Manasa. Pretty much you have covered most of the my profile items. Apart from this, we are also working with both central and state government on some of the projects. Well, why we need to focus on cybersecurity? Bharat is facing hell a lot of problems, and the attackers are from all the directions, right? So if we are not going to monitor, prevent, protect, and predict the attacks, it will be disaster for Bharat. And we are already witnessing, because of the geopolitical issues, if you look at, there are a lot of attacks, not only on ground, but also in the cyberspace. And at Astaksha Labs, we are committed to prevent, predict, and protect the nation, especially in the cyber space. All right, so we have witnessed a lot of attacks in recent, years, especially on the critical infrastructures and other sectors as well, including the defense, healthcare, government, and the automotive sectors. So this presentation, predominantly we are focusing on the defense as well as automotive sectors. Before that, let us have a look at a couple of case studies, the attacks that we have witnessed worldwide. In one of the attack, the remote attacker was able to successfully compromise the Nissan Leaf automotive or car. The research was conducted by PC Automotive. Let us have a look at that. And with this hack, the researchers were successfully able to control the car remotely. Let us have a look at the video.
All right, I'm starting monitoring now.
Before that, is my screen visible, and are you able to, is the audio clear?
Yes, sir.
The
Yes, sir.
screen is visible and we can hear your voice, sir. No problem.
Not only voice, what about the video?
Yes, sir. Video is also very clear and we can.
Thank you very much.
All right, I'm starting monitoring now. Tracking, start. Okay, GPS tracking. Perfect. Right, fully controlled. All right. Can I send one control? Okay, send that. I'm sending your comments now. Right. Okay, I'm sending my comment now. Okay, steering, start. Steering wheel, send.
All right, so in this video, the attacker was able to connect to the car remotely, and he was successfully able to control the vitals of a given car. Right, it could be, the engine, it could be the brakes, it could be the mirrors, indicators, horn, everything. Right. We will look into the details of this attack later. But let us also have a look at the other type of case study where the CAN protocol was abused by the attacker, right? Unfortunately, the video is long enough, so I'm going to brief you all how the attack was carried out. The attacker was able to connect to the CAN bus, and by making use of couple of components like Arduino and NXP boards, he was able to inject malicious packets, CAN packets. This is the diagram for that. And if time permits, we will also show a simulation of this attack. Here, typically CAN bus is used to, send the packets to control the units from the ECU and to the UCU, where the attacker can send maliciously crafted packets and inject the CAN bus so that the ECU will be under the control of the attacker. These are the maliciously crafted packets. Right. So we saw one of the remote attacker controlling the car. In the second case study, we saw how the CAN bus can be abused. In the third and upcoming attacks that we are witnessing are the AI based, right? Nowadays, you take any product, they come with a statement by saying like it is AI powered, whether it is broomstick, even broomsticks are like having AI powered facilities or features. The similar AI component was included in one of the Tesla car, and based on that, the cruise control will automatically be monitored and controlled. In this, the attack, the adversary was from the external component, right? The AI model was able to read the signals or the signal boards on the street, and based on that, the cruise control will be automatically monitored and controlled by the AI module. So the attacker was able to introduce some adversary. In this case, the actual board had 35 miles per hour. But if you look at the image carefully, there is a cellophane or the tape, the black color tape that is attached, so that it looks like instead of 35 kilometers or miles per hour, 85 miles per hour, right? Now what exactly happens if this is introduced?
Shivangi is holding up our adversarial 35 mile per hour speed limit sign, with a small piece of black tape as the only modification. We start the car moving forwards, and the Mobileye camera immediately incorrectly identifies an 85 mile an hour speed limit sign. Now we engage traffic-aware cruise control, and with our feet entirely off the gas and brake pedals, the Tesla begins to accelerate to 85 miles per hour. We cut it short at approximately 50 miles per hour for safety reasons.
Looking at these case studies, it's very scary, right? The attacks on automotive sector is expanding, and we should be very, very careful in coming up with the components or developing the components on the automotive sector. What is the need for looking at all these case studies? What is the need for automotive system security? Number one, for civilians, the utmost importance is to must be given to the safety of the passengers, whoever, like whether the driver or the passengers. We need to make sure like they have trust on the vehicle which they are driving. Not only that, there are cases where the personally identifiable information of the owner as well as passengers were compromised, and they were abused by the attackers. So the data privacy plays a very, very critical role. Yesterday, I was in one of the Data Security Council of India meet, which was held in Bengaluru, where the defense, the aeronautics, Bharat Electronics, and various other cybersecurity companies were present. They emphasized on the data security of both civilians as well as the nation-based data. And of course, like if these automotives are compromised, it creates a lot of issues on the roads. The safety of pedestrians, not only that, also to the critical infrastructures of Bharat. And most importantly, the trust in the technology, right? People who are walking on the street, who are driving on the roads, they need to trust the technology, especially automotive systems. Not only that, when it comes to the business sector, the financial and reputation of a given OEMs or car makers heavily depends on how secure their automotives are. As well as it's a mandatory that these companies, they have to abide by regulatory compliances. And more importantly, they need to continue with the business, right? And now the critical part of Bharat is defense. All these automotives are not only, they are all dual purpose. They are not only used for civil purpose, but also for defense, right? Especially whether it is tankers or military vans or drones or submarines, aeronautics. In all these sectors, if there are, remote attackers controlling these automotives, you can imagine like how mission critical these operations will be, right? So it is also important to look at the defense part or sector as well. And also there are cases like once the military or defense automotives are compromised, posing a huge espionage attack, that is spying, right? So the security on these defense vehicles will prevent such espionage attack. Not only that, the sabotage or the destruction or disruption in the operations of these automotive sector in defense. Basically, the objective here is why we need automotive security is because we need to have resilience against the cyber warfare, especially in the defense sector. All right. So before we jump into the case, internals of automotive security, it is very important for the participants on this ATAL FDP to understand some of the fundamentals of cybersecurity. I'm not going to get into the the nitty-gritties of these concepts, but cybersecurity is standing on three pillars: confidentiality, integrity, and availability. Let us look at the fundamentals of cybersecurity. The confidentiality heavily depends on the encryption, right? Encryption and decryption methods, and some of the basics of network, the integrity or the hashing part, as well as digital signature. This is very important for the data that is transmitted or the firmwares on the automotive sectors, how they are updated securely, as well as availability of services on these automotive sectors. Let us look at what is encryption. Like we have been hearing all this, the paragraph of encryption, conversion of plain text to say, cipher text. But for that, we need to understand what exactly happened. Let us consider the vehicle telematics, which we collected from one of the research paper. In this, we have the telemetry data collected by the OEMs, right? It could be the date, time, EMS systems, or the ABS sensors, the fuel level, brake oil. These are some of the data that are continuously collected by the car manufacturer for various diagnostics and improvement of their services, right? Now, let us consider this telemetric as a plain text. If this plain text, we are going to encrypt using the secret key by using some industry standard encryption method. In this case, can you see the difference between the plain text as well as the cipher text here below? So in the plain text, the attacker will be able to see all the data which are in ASCII representable. But in case of encrypted data, attacker, even though is able to capture the data, is unable to see like what are the information that are transmitted from the vehicle to the telemetric server, right? In this case, we have created this plain text and cipher text by using AES algorithm with the CBC mode and with 256 encryption key length. And at the receiver's end, the encrypted data can be decrypted by the same key. This is in case of symmetric key. This is how the decrypted data looks like, right? So we are looking at encryption and decryption. Don't worry, we will look at like what are the importance of encryption and decryption in upcoming slides. But this is how actually the encrypted and the plain text looks like. In fact, in 5-day workshops, we will be teaching the faculties on how to perform this encryption and decryption methods. Due to the time restriction, we are just showing this snapshot of all these concepts. Now, let us look at how if the same file is transmitted over the network, the snapshot shows the packets captured of the same file which is sent without encryption. In this case, we are using FDP protocol, which is not secure. And if you look at the packets, one can be able to easily read all this information. Suppose if we are using the secure protocol, this is how it looks like. The attacker will not be able to see what is the actual data that is sent. Okay. The next very important part of the CIA triad in cybersecurity is the integrity of the data. Now let us look at what is this integrity. Now suppose this is the data that I need to send to telemetric server. I'm going to calculate the hash mathematical value for the given data. In this case, we are using MD5 hash. Now, suppose if I'm going to modify, if the attacker is going to tamper the data instead of brake oil here, if the attacker modifies that to engine oil, now there is a data that is tampered. In that case, the integrity of the data is broken. And again, like we are going to calculate the MD5 hash. If you look at the slide, it shows what was the actual data, the legitimate data, what is the hash value for that, and what is the hash value for the tampered data. Looking at the hash values, we can easily say whether the data which was transmitted or received from the car was tampered or not. The other important concept in cybersecurity is the digital signature. Typically, this is used for verifying whatever the firmware update that we are going to do on the car systems or automotive systems. Now, let us look at how this digital signature works. Typically, the data is sent from the sender, and we are going to calculate the hash. We already saw like one of the hashing technique, that is MD5 hash, and then the hash value is calculated. This hash value for the legitimate data is encrypted using the private key of the asymmetric key encryption method, and that hash along with the data is transferred via network. So the data as well as the encrypted hash value is transferred, and at the receiver's end we need to check whether it was tampered or not. So again we are going to calculate the hash for the data that was sent. In this case, the Word document symbol that you are looking at, we are going to calculate, as well as we are going to decrypt using the public key and check whether the hash matches, thereby calculating or verifying the authenticity or integrity of the data. So this is a typical digital signature working. Let us see like how these basic concepts of cybersecurity help in securing the automotive sector. Typically, like there are tools which can verify whether the data was tampered or not, or the signature is verified or not. Suppose in this case, the data is modified. Suppose if the data is modified, this digital signature will fail. And probably all of you might have seen all these logos or symbol, right? The digital verification of a given document. And suppose if it is not verified, the symbol like question mark. Right. This is how exactly the private and public key looks like. And these are used on the plain text to create the digital signature. And there are tools which will verify whether the document which was signed is valid or not, or legitimate or not. In this case, we had modified, the data was tampered. Obviously, the verification of digital signature will fail. The other important concept of CIA triad is the availability. Probably you would have experienced the availability. In this case, like the case study is, we are looking at our own website, Ashtaksha Labs website. The website must be available for any user. If the user clicks on or types ashtakshalabs.com on the browser, this is the availability for a typical user. Now, suppose if the attacker is sending n number of packets by creating a sync flood or any, there are multiple ways how we can have this denial of service. In this case, millions of packets are sent to the server, so that if the user clicks on the website is not operable, thereby creating the denial of service. Right. All right. Now, after looking at the fundamentals of cybersecurity, that is the confidentiality, this is achieved by encryption and decryption methods. Integrity of the data, that is by which is achieved, as we saw, using the hashing techniques, as well as availability. Now let us look at the various attack vectors the automotive sector is experiencing. Attack on a given car can be from various sources. Typically, we call it as attack vector. In this case, telematics. The telematics are it is the infrastructure where the car will be sending some critical information to the cloud, and which is available for not only for the car manufacturers, but in some cases it is available even for the car users. And the infotainment or ECU, electronic control unit, EV charger, CAN, mobile apps, specifically vehicle mobile apps, and the GNSS, that is Global Navigation Satellite System. So we have cherry picked only these attack vectors so that it will be easy for the participants to understand. Anyway, like most of us, we are driving the latest cars which will have all these features. So let us look at the attack vectors in detail. The telematic control unit, typically it collects the vital information, whether it is fuel, whether it is GPS location, whether it is the operations of the engine. All this information is collected and shared to the cloud infrastructure. From the cloud infrastructure, the data will be stored by the car manufacturers or the service provider, right? And there are methods where the user as well as the car manufacturers or the OEMs, they can access this data. Typically, there are some REST APIs or the APIs, application programmable interfaces, where we can access all this critical data. Now, we have seen many such attacks by compromising any of the unit here. In this case, like the telemetric control, the TCU can be compromised, where the attacker can gain access to the TCU and manipulate the data, or the cloud, the hosting cloud can be compromised by the attacker. There are various attack types where the cloud can be compromised, or the the database server or the MS SQL, you name it, and the APIs which can be abused, or the devices which are accessing this data, even they can be compromised. One such use case or case study is like the telematic APIs and the infrastructure was compromised, impacting more than 350 million cars. And this is the the news article on that. If you look at carefully, you take all the big players in the automotive sector, whether BMW, Ferrari, right, Nissan, Rolls-Royce, all these companies were compromised. The other type of attack vector is the infotainment. I believe like most of you who are driving cars, you would definitely connect your mobile via Bluetooth. There, am I audible?
Yes,
Yes, sir.
audible.
Yes, sir. You're audible, sir.
Right. Typically, what we do is like we are going to pair the mobile device with the infotainment of a given vehicle, right? And this happens only once. We are happy to pair that because we want to answer calls while we are on the wheels. Or there are some applications which I can play to play music like Spotify and various others. So if my mobile is connected, there are a lot of activities that I can perform on the connected vehicle. Now, what exactly happens if this is paired? On the infotainment system, I can view the call logs, I can view the contact list, I can view the applications, right? Thereby, the infotainment, because it is connected to ECU, via infotainment, I can also compromise the electronic controller unit. And this is exactly what happened in one of the attack, where the attacker was able to compromise the open source or the framework or the SDK, which is used to connect the Bluetooth. In this case, Open Synergy Blue SDK, which had 4 vulnerabilities. Collectively, they named this vulnerability as Perfect Blue. Now, once these vulnerabilities are exploited by the attacker, he can easily gain access to ECU. Thereby, he can eavesdrop what are the conversation that is happening on that car. He can easily, there is a data theft. In this case, the contact list, the call logs, or the other, personally identifiable information of the user, remote manipulation of the ECU, and deeper control, whether it is engine, brake, as well as the persistent access. Because once a mobile device is connected, the moment you get into that car, again it will be connected automatically without pairing, right? So these are the consequences of the connected mobile via Bluetooth, and this is typically happening via infotainment systems. Believe it or not, 350 million vehicles were compromised. You can imagine what can happen to the vehicles in Bharat. It is happening. It's just that we have not come across such attacks, or we are not aware that these attacks are happening. The other type of attack vector is electronic, charging. Nowadays, there is a lot of push to EV vehicles. These charging points are also vulnerable. One such attack that we have seen is how the charging firmware can be compromised. In this case, the security research team of Placidity, they were able to identify the vulnerability and compromise. There was a vulnerability in one of the V2G, that is vehicle to charging gateway, right? This is a typical integer buffer overflow, which again resulted in the heap buffer overflow. I'm not going to use the security jargons here, but in a nutshell, how the charging points can be compromised, thereby bypassing the charging payment gateways, as well as stealing some of the private cryptographic key, which can be used to impersonate legitimate charging stations. And sometimes this compromise can also lead to crashing of electronic vehicles. These are the, the details, the technical details of how this attack happens. I'm going to skip this in the interest of time. But again, like, there are n number of charging stations which were compromised. Now coming to very important aspect here, the CAN. I believe the topic is on real-time and automotive CAN applications, right? In 2019, I was part of this hack in the box, which happened in Abu Dhabi, where one of my fellow researcher, he demonstrated how the CAN can be abused and attacker can control the car system, right? I'm not going to get into the nitty-gritties of CAN working, because I believe like you're all experts in that. But basically, the CAN was used to communicate with various components of the automotive items. And this CAN, when it was identified, or when they came up with the CAN concept, they did not consider the cybersecurity element, right? This was in 1986. Nobody knew that how this can be used and abused. In this case, typically the lowest ID on the CAN bus will be the highest priority, and airbags, ABS, they fall into lowest ID, and the door lock, infotainment, and other things, they fall into highest ID. Basically, the attacker or the researcher from TCS, he is successfully able to connect to given car via CAN, and he was able to manipulate the CAN packets, inject malicious data. This is a snapshot of what we had conducted at Astaksha Labs. On left hand side, if you look at all this hexadecimal number, these are the CAN packets that we were able to capture. On the right hand side, the topmost, this is the simulation of the car, and below that it looks like a gaming console, but this is not a gaming stuff. This is the actual simulation of the car. And in this case, attacker can send a packet with 19B to forcefully unlock the doors. Right. Give me a second. Let me see like if we can show the demo on this. Yeah. One second. Is my screen visible?
Yes, sir, visible. Hello, sir.
Yes, sir.
Are you able to see the Kali terminal?
Yes, yes. Yeah.
Yes, sir.
Okay. So here we are simulating the CAN. We are simulating how the dashboard of or the speedometer of a car looks like. This is the control that is used. And we are going to dump the packets. Can you see here? Right. If I press up, can you see? This is typically the data that is transferred via CAN. We are simulating by using vCAN, virtual CAN. This is the data how the car will be getting from the CAN bus to ECU. And now, like using the simulator, I'm going to increase the speed. Are you able to see this?
Yes, sir.
Yes,
I am at 80 kilometers per hour, 90, 100, and then I'm going to I'm operating the indicators. Can you see that?
Yes, sir.
Right indicator, left indicator, right? Let me open the door. Can you see the doors are getting opened?
Yes, sir.
Now, how I am able to do this is by sending the data via CAN to the ECU, right? Now, this is the normal operation of user. Suppose if the attacker gains the access to the CAN, typically that is done by onboard diagnostic device or the port. If you are looking at the right side, the doors are closed. Now, by sending one packet, if you look at the left-hand side, the can, send, we can, and this is the packet, this is the data that I'm going to inject. Can you see all the 4 doors are open now? Right.
Yes,
So
yes, sir.
this is the similar technique that attacker used in the video, which I showed in the case 1. Right. Just a minute. Let me go back to presentation. Is my screen visible?
Yes, sir, it's visible.
Now I'm showcasing how most of the thieves, they were able to inject the can by using the similar method. They were easily able to hack and steal the cars. Right. And most of the cars are having these vulnerabilities. Right. One can easily get into can via various methods. In this case, he was able to get in using Bluetooth speaker case. Right. The other attack vector is we are used to downloading the applications, whether it is on mobile or on connected vehicle for various purpose, whether it is YouTube, navigation or music, contact and video players, right? There are a lot of applications, smart application meant specifically for connected vehicles. Now, suppose if the malicious applications are downloaded onto the car, what are the consequences? In fact, last month we demonstrated one of the fake app of SBI in Tumukuru in collaboration with Tumukuru Smart City and police, where a fake SBI app can gain control of a complete mobile device. A similar thing will happen if you are going to download the APKs or application from unknown sources. Right. One such use case was one of the user, he was able to download the app because it had additional features. And I believe, like most of us, we are used to download APKs from unknown source because it is going to beautify my photos or videos, right? Or editing stuff or gaming apps without even witnessing whether or without even checking what are the permission that this application is requesting or what is the source of this application. And in most of the malicious application, typically they will not be on legitimate source or store. If we are going to download using browser or unknown source, these are the consequences. It is definitely going to steal all your data. There are a lot of frauds that are happening. It's a ransomware where the device will be compromised and the access to user will be cut off until the ransom is paid. There are a lot of adverts where unnecessary advertisements will be shown on the infotainment, as well as Trojan, backdoor, where the attacker will have complete control on your car. So please be very careful when you are looking at any of the unknown source for your automotive, especially cars. And this is the case study, like in 2024, there were a lot of malicious apps to the connected cars, which led to various such attacks. Next attack vector, which is very common, right? We are all using, whether it is Google Maps or other navigation systems for commuting and reaching from point A to point B, right? Now, what is this global navigation satellite system? Typically, it is used for day-to-day applications. It is also used for disaster management and safety purpose, tracking and logistic. And this is very important, like it will sync the time as per the satellite, mapping and surveying, and more importantly, navigation. There are multiple use cases of this navigation system, but if the attacker is able to control or replay the attack, there are a lot of cases that we have witnessed. One such case is the attacker can continuously send the similar signals as that of GNSS, thereby jamming the actual legitimate signals. We call it as GNSS jamming. Or the other type of attackers, he can send a specific signal where he had captured from somewhere else, some legitimate signals. Typically, we call that as GNSS spoofing. One such attack was on Tesla, right, where the car automatically was, parked, and I mean, like it was driven to the on the footpath, and it was parked. There are a lot of consequences of this, security issues on automotive sectors. The concept or the theme of this is RTOS, real-time operating system. One of the characteristics of real-time operating system is the responsiveness of the operating system. Now, if you look at the responsiveness in the automotive segment, suppose if I apply the brakes, the operating system must have that capability to respond to that in a timely manner. In this video, like the two cars are approaching, there are a lot of AI components which will detect and apply brakes immediately, right? Now, most of the adversaries or attackers, they are going to compromise the responsiveness of automotive segment. What will happen if that is compromised? Major disaster. Right. The other characteristics of RTOS is determinism, meaning the feature that was created must operate without any ambiguity. In this case, there is a airbag which was designed, and the ECU must open that airbag in a deterministic manner. But the adversaries, they are going to compromise the determinism. If that happens, instead of opening the airbags, you look at the consequences. All right. Now, looking at the case studies, looking at the demonstration or simulation, one must carefully look at the automotive security from all the 8 perspectives. Remember, like in the beginning, I spoke about 8 directions of Astaksha Labs, but that is for a layman. For tech savvy or technical people like you, each and every dot has a very meaningful cybersecurity concept, hardware level, right?
Sorry to interrupt, sir.
Yeah.
I have a question to ask.
Yes.
What is the difference between GNSS spoofing and GNSS jamming?
All right. So GNSS spoofing is you're capturing the data from somewhere else, you're modifying that signal, and then you are replaying that, and you're saying like you are the actual, the signal is from the legitimate satellite, but it is not from the legitimate satellite. The attacker is replicating the signals from his attacker device. That is spoofing. Jamming is you're continuously sending the signals. You're not allowing the automotive device to get the legitimate signals from the satellite.
Okay, sir. Thank you, sir. Like how the intrusion is being detected in automotive systems, if at all, is there any intrusion?
We will come to that, madam. I mean, please, in the interest of time, we will complete the presentation, and please hold your questions. I'll be more than happy to address all your concerns or questions.
Okay, sir. Thank you.
Thank you very much. Thanks for your understanding. Right? For any electronic device, there are multi-level security that we need to focus on. The first layer is hardware layer, right? Because if the cybersecurity is not considered at the hardware layer, it is very difficult to prevent and protect on the upcoming layers. Let me give you the brief of what are the layers. Hardware, firmware, operating system or platform, application, network, cloud, data, and human. These are the 8 dots that we will be focusing on. So if the hardware level components are compromised, it is very difficult to protect at the application or operating system layer. So at the hardware level, we need to make sure it is tamper resistant, right? These are the sophisticated techniques used by the attackers. There are side channel attacks. There are various other types of malicious components embedded in the or included or assembled in the at the hardware level. They are very, very difficult to detect and prevent. And this is one of the reasons why we are very, very cautious in importing certain components, hardware components from our friendly nations like China and other, who are manufacturing the chips. This is the reason like why our Honorable Prime Minister Shri Narendra Modi ji is pushing a lot on indigenous components, especially at the hardware level. I believe like there are, we are spending about 7.5 lakh crore rupees on chip manufacturing because we want to be self-reliant and self-sustainable model. At the hardware level, we also have, key management, because if the encryption key at the hardware level is compromised, then all other layers are compromised. Random number generation is very important for various security related activities and hardware based access control. So these are the components. I'm not going to name all the components at the hardware level, but I'm going to give you some of the very important concepts. So these are the concepts that must be taken care when we are coming up with the automotive hardware or designing and developing automotive hardware. The other layer is the firmware. Typically, like on your mobile devices, you will be seeing there are a lot of firmware updates. What are these? They are actually patching. The OEMs are patching the vulnerabilities which are identified, and that has to be upgraded or updated in a very secure manner. There where at the firmware level, the concept of the code integrity, secure boot, and the secure update. This is where the digital signature which we saw comes into picture. I had seen one attack where the OEM did not have the digital signature on his, on the firmware, so that the attacker was able to modify the firmware and inject malicious code, thereby compromising the electronic device at the firmware level. And once compromised at the firmware level, again, gone case. We cannot detect and prevent at the application or kernel level or operating system level. The next level of security that we must be focusing on is the operating system, especially in the RTOS. These are, number one, authentication for the user. Only the legitimate user must be able to operate that or log into that operating system. Kernel protection. In most of the unsecure RTOS, the kernel will be, or the operating system will be modified. There are various methods to protect such illegal modification of the operating system. We need to introduce that. There are like real-time kernel protection. There is, static kernel protection. There are various methods. We will, if time permits, we will discuss on that. Process isolation. Suppose if there is a process which is controlling the engine and another process which is controlling the headlights, we need to have process isolation so that there won't be any process injection compromising the critical processes, as well as patch management system, right? The other layer is application. At the application level security, typically we mainly focus on the self-protection of the processes or the application. And also we need to have web application firewall. Remember, like we saw two attacks where the remote attacker was successfully able to send the malicious packet. Suppose if we have web application firewall, we can block such illegal or malicious packets. Of course, like antivirus and endpoint security. At the network layer, the concepts are like we need to have network layer firewall. This is where partially will answer your question, madam. Like we can have intrusion detection and intrusion prevention systems, which will identify if there is any intrusion happening. There are various ways. There are signature based. There are anomaly based. There are behavior based detections that we can employ or deploy. Network access control, we can clearly mention who can access the components of ECU, who can access the CAN bus. And of course, like virtual private network, thereby having some layer of protection so that we can block unwanted network traffic. Over the air updates, this is very important because most of the cars nowadays, they are having this facility where the OEMs or the car makers, they are able to update the system over the air. I mean, like whenever they want. Typically, they are using some network protocol, whether it is 5G, 4G, or cellular network. We also need to make sure the cloud is secure, right? And this happens by having identity and access management. Only the OEMs or the user will be given access to the cloud components. We also need to have the cloud workload protection by having the virtual machines protection, as well as Dockers or containers. Very important. This is what we are lately witnessing. There are a lot of DDoS, distributed denial of service. We need to have at the cloud level how to prevent such DDoS attacks. Of course, data, right? If you look at, most of our cars are having our personally identifiable information, whether it is the owner name, the car owner name, mobile number, or the vehicle number. Is a very important concept of vehicle ID. Some of the vehicle manufacturers, they will have this ID on the windshield, right? And this information is utilized or sent via telematic to control and to diagnose certain activities. What if this data is, not encrypted or not masked, right? In this case, like Ramu and Shamu, they are the owners. And you look at the information, the personally identifiable information, whether it is mobile number, whether it is car number, everything is sent if we are not going to protect that data. So at the data layer, we need to have encryption methods so that the attacker, even if he gets access to this data, is unable to identify what is the type of data that he is getting. Data masking, I believe, like nowadays, if you look at the Aadhaar card that you are going to download, some of the information will be marked as X, right? The data masking will happen so that even the attacker is able to get the data. He doesn't have the complete information. Tokenization or anonymization is very important concept. Instead of sending Ramu and Shamu, I can have a token which is mapped to Ramu and Shamu, so that the attacker doesn't know what is the data that is sent, thereby protecting the personally identifiable information. Now the introduction of DPDP Act, Digital Personal Data Protection Act, there are a lot of issues that OEMs must be considering. Suppose if the personally identifiable information is compromised, the fiduciary, meaning like the data owner or the company who is providing the service, they are liable, and the penalty is up to 250 crores. I'm sure like going forward, it will be very, very difficult for the service provider and the OEMs of the automotive sector. And of course, like even if the data is captured, we need to have a secure way of erasing data, right? Suppose if the car or the electronic device is stolen, it is very easy for attacker to get the confidential data. Remotely, one should be able to erase that confidential data. So we need to have data erase mechanism. We need to have data backups, because if in case of any ransomware attack, we as user must be able to get back our data without paying the ransomware from the backup. And of course, data loss prevention. How can we have data loss prevention on the defense vehicles, so that even, I mean, like we can prevent some mission critical data getting leaked to the attacker. And of course, all said and done, if the user is not educated, right, if the awareness is not given to the user, then gone. Like human, they are the weakest link in the chain. So it is very important, like the human level security, where we have such FDPs and security awareness programs, so that the users of the automotives are aware what are the attacks that we are facing, what are the consequences, and eventually they can secure by having strong, authentication methods, by strong password policies, having multi-factor authentication. Even if the attacker is able to get access to the automotive car without multi-factor authentication, if he is unable to on the car or power on the car, it's of no use. So there are multiple ways that we can have human level security, as well as we are not only users. I believe like some of you are working on real-time operating system. You are coding, you are developing certain modules. We also need to employ secure coding practice, because if you look at all the case studies, there were vulnerabilities which were exploited by the attackers. What are these vulnerabilities? Because the developer did not pay attention to the bugs, they resulted in vulnerabilities. Eventually, attackers were able to compromise a given system by exploiting these vulnerabilities. So secure coding practice must be employed. And of course, very importantly, I believe like it is important for all the automotive engineers, especially who are from the mechanical background. They must be aware what are the security aspect and have domain specific technical training. So cybersecurity will cut across domains. So specific technical training on cybersecurity for all these automotive developers or the mechanical candidates will help to have a secure, automotive sector and Bharat. So altogether, let me summarize. Cybersecurity must always be looked at multi-layer, that is hardware level, firmware, operating system, application, network, cloud, data, and human. With this, let us also look at some of the do's and don'ts as developers or designers of real-time operating system, especially in the automotive sector. We need to have in-vehicle communication which is confidential. Suppose if I am transmitting data to the engine part, that must not be visible to the headlight part or component, right? In-vehicle encryption methods will definitely save here. And all this must be considered at the design level. It's not that I'm going to come up with a car, I'm going to have all the features and then try to, inject or include the cybersecurity component. No, it has to be done at the design level. When we are designing the features, when we are designing the components, we must take care or consider the cybersecurity. And this includes, whether it is OBD port security or Bluetooth security, vehicle intrusion detection system. Madam, this is what I was talking about. There are vehicle intrusion detection system available, which are paid, as well as USB security, because we have seen many air gap systems, right? One classic study was the Stuxnet, where the Iranian nuclear power plant was compromised. This facility or infrastructure was air gapped, meaning all the centrifugal components, they were not connected to external network, but they were compromised using the malicious USB, which was injected or inserted, right? We need to follow the USB security as well, thereby limiting the attack vector and hardening the remote access or interfaces. The other important concept here is, even, nowadays, most of the automotive, car manufacturers, they are moving from CAN. They are having network security, that is like HTTPS and other protocols which have network security components. And also we need to segregate the critical component network as well as the other, must have and nice to have components. It's always better like we segregate the network. That will save a lot of, save us from a lot of attacks. Of course, like from a car service point of view, whenever we leave our cars to the service station, please upgrade your firmware, right? A regular monitoring of firmware updates is very important. Security by design, this is already covered. And whatever the authentication that we are giving for the various components of infotainment or other car components, we need to employ very strong authentications, right? Please tell me, like, how many of you are using the same password for your Gmail, for your Facebook, or any other social media? There are a lot of cases like one social media compromise can lead to other, compromise, other application compromise, because we are using the same password to all these components. Please avoid that. And going forward, vehicle vulnerability assessment and penetration testing. This is very important. Okay, I have 20 more minutes. I'm going to, wrap up in 10 minutes, and then we can have 10 minutes of Q&A session. What are the do's don'ts from a user perspective? Please be very, very careful when you're installing third-party application without verification on your vehicles, as well as do not give access to your infotainment to any other Bluetooth devices or cars. I mean, like that being said, when I attended Data Security Council of India meeting yesterday, I had to hand over my car to the valet parking guy. I don't know whether he has connected his mobile to this, because he had access to my infotainment, as well as he was able to successfully pair his mobile. We should be very, very careful in handling, or handing over the vehicles to the unknown person. And of course, don't delay patching, whether it is patching of your vehicle operating system or the applications. And this is for the developers. Please don't use weak or static encryption keys, right? I think most of the automotive car makers, they are nowadays moving to EEPROM, electronically programmable ROMs, instead of burning the encryption key on the hardware. Thereby, they have certain security feature. Even if the encryption key is obtained by the attacker, the OEMs can update that. They can revoke the keys and update the encryption keys. All right. In the interest of time, I'm going to stop here. Thank you very much for your patience, listening, and to your time, especially on the weekend, the Friday night. Now I open this platform to Q&A.
Hello, sir.
Yeah.
Embedded systems, the design metric parameters, constraints on design metric parameters, it's very rigid, especially like with respect to power, with respect to cost. Like it has to be the exact fit of how much over it's just required. So especially for the low power embedded system, is there any specific encryption methods?
All right. So it's very interesting and challenging question. Right. So security always comes with its own price. Right. There are, depending on where your electronic device is used, you can have customized security. Instead of, like in this case, we used 256 bits. There are lesser bits encryption key which are available, which are fast enough. Number one. Number two, there are security on chip, SOC, or system on chip. There are some hardware level, the key length of this is lesser than the mentioned key length. We can reduce the key length and have that security at the hardware level for a lesser cost. But keep one thing in mind, it depends on whether you're using this vehicle for civil purpose or for defense purpose. Because if you're using this for defense purpose, we cannot compromise on the security, right?
Yes, sir. Yes,
Thereby, we have to have a perfect, or I won't say perfect, we need to balance the cyber security feature and the operational or functional feature, madam.
Okay, sir. Thank you, sir. One more question, sir.
Yeah.
How early in the design process should cyber security be considered in the design process of embedded system? How early?
Right. That's again like very interesting question. Like whenever we are designing any, whether it is hardware or software, at the requirement level, right? If you are aware of the software lifecycle, requirement analysis, requirement elicitation, requirements gathering, we need to incorporate security features at the requirement level. What is the requirement? I mean, like security requirement for novice user. What is the security feature that I can provide to advanced or expert user? At the requirement level, if we are incorporating the security components, that will trickle down to something called as threat modeling, right? What are the components which must be secured? What are the components which we can have without security, right? This comes at the architecture level, madam, right? So security must be considered at the initial stage of any development, but at the hardware level, we need to have these concepts at the chip design level. Unfortunately, most of the security chips we are importing. I think there is a very urgent and strong need that we need to start manufacturing chips which have security in it.
Okay. Yes, sir. Thank you, sir.
Sir, I have a question. Like, how can public key and private key be applied in real automotive communication systems, sir?
All right. See, as I mentioned, like there are some information which are transmitted and received by the telematics and with other control units of a vehicle, right? If we are including the hardware level security, which will typically manage the key. At the hardware level, we can store the encryption and decryption algorithm as well as keys, right? And the hardware level security component or hardware level hardware security module is reasonable. I mean, like responsible to securely store these keys on a given device.
What is the common technique they will be using, sir?
The key management, madam, like all these keys will be updated when we are updating the car firmware, right? There we are going to write these encryption and decryption keys at the hardware level, and this will be utilized by the hardware level component algorithms, encryption algorithm, to encrypt and decrypt data. And this is what will be used by the RTOS in communicating or transferring and receiving the data that is sent from the car device. One second, let me go to that slide. Just give me a sec.
Sir.
Is my screen visible?
Yes, sir.
Right. See, the TCO is responsible for transmitting the data and receiving the data from the cloud or the server, right?
Okay.
If the car manufacturer or maker, if they are encrypting the data before sending, and if they are having the system on chip which contains security algorithms like EES, RSA, as well as respective keys for this, then we can have security on the data that is sent and received. And this typically is part of hardware security module or hardware security platform.
Okay, sir. Sir, among all the levels of security, like hardware, firmware, OS, application, network, cloud, and data and human, so which one is the most vulnerable, sir, today?
Okay, that's a very good question. Human, doctor, because if the human is not aware of all these security issues, definitely, it is very easy for attacker to do the social engineering and compromise the user of automotive sector, thereby compromising everything. Despite, if let us take this analogy, very crude analogy. Suppose I'm the owner of the my residence or my home, and I have a door which will prevent attacker entering my home, and I have a lock. I'm going to lock this, and if I am going to leave that key next to the door, like irrespective of me having security features, if the user is not abiding by the security rules, it is very easy for attacker to get into the device or home. So in my opinion, humans are most vulnerable because they can be easily tricked. There are a lot of social engineering techniques. One such which I mentioned, like the SBI application, right? The fake SBI application was shared via WhatsApp, and with the social engineering message that if you are not going to update your Aadhaar via this APK by tonight, your account will be blocked. Most of the victims, they downloaded that, thereby giving access to the attacker. I mean, like the access to that device. So in my opinion, humans are most vulnerable. Apart from that, the data. Whenever we are sharing any data, we should be very, very careful. Nowadays, like if I say like you're going to get 50 rupees rebate, give me your email ID, give me your password, or give me your mobile number, we are happy to share that. What if this email ID and mobile number, if they are linked to the telematic infrastructure, so attacker can gain easy access by using your mobile number. In one of the attack, which in this case, the case study was the OTP. One second. In this case, the OTP of user was sent to a given email ID. Now, if my email ID is compromised, the OTP for this car can be obtained to or received via email, and thereby giving access to this entire car via compromised email, right? So it is very, very important to secure our personally identifiable information. And I believe, like, see, this is very scaring. Whenever I used to travel outside Karnataka, it is most of the, I mean, especially like Tamil Nadu or Goa or Andhra Pradesh, the other state police will definitely check the emission certificate. And if I want to get this emission certificate from any of the service provider, if I give my vehicle number, this guy from his system is able to easily get what is the name of the user, what is the mobile number, sometimes email ID, and address of the user. All this information is available. And there where DPDP Act comes into picture by securing, but the onus is on the owners of the car. I should be vigilant and I should be careful in providing my personal data or my data which is related to car.
Okay, sir. Understood, sir. Any questions from the participants? Dear participants, so if you have any questions, you can ask to sir.
Well, that being said, I know given the 90 minutes, which is very, very short time to convey most of the security concepts. Typically, what we do is we will have complete 5-day workshop
Yes, sir.
to cover all the aspects of security with the hands-on. But
Okay, sir.
given this limited time, I know you will have many questions. Even if you are unable to ask that as of now, please connect with the coordinator. You can send the all your queries and questions, and coordinator kindly share that with us. We will be more than happy to address your queries, because end of the day, we are citizens of this wonderful nation, and it is our duty to secure the nation, right? And cybersecurity is not responsibility of either security vendor or car manufacturer. It is a collective responsibility. We all need to collaborate and contribute to the security of the device, your organization, and the nation. Thereby, we always live with a note that together we stand, divided we fall. Right? So let's join hands in securing our automotive devices, our electronic devices, thereby securing ourselves, our loved ones, and the nation.
Definitely, sir. Definitely. Um, so, uh, on behalf of all the participants, I sincerely thank Mr. Nandi Dharma Kishore, sir, for his valuable session. Sir explained the different cyber attacks like remote attacks, scan injection attacks, AI based, and GNS attacks, along with the importance of safety, data privacy, and multi-layer security. So his clear explanation of encryption, RTOS security challenges, it gave us practical insights into automotive cyber security, sir. So we are truly grateful for your time and knowledge, sir. We are truly thankful for your time, sir. Your clarity in simplifying the complex concepts and for inspiring us. Thank you once again, sir. Thank you very much.
Thank you, one and all. And I know it's a Friday night. Enjoy your weekend and always stay safe. And those who are interested in, cybersecurity and automotive or electronic security and embedded security, as well as AIML security, we are here. We are the resource of you and the nation. Please feel free to connect with us for your research or any other cybersecurity and AIML related activities. Thank you very much once again, SSIT management and Dr. Manasa, Dr. Komala, Dr. Ghouse Ahmad, as well as the management of SSIT. It's a great privilege to be part of this ATAL FDP. And I hope we all will share the knowledge for the betterment and, to have a resilient Bharat and have a wonderful weekend. Thank you very much. Bye for now.
Thank you, sir.
Thank you, sir.
Thank you once again, sir. Thank you so much, sir. Thank you, sir.
Bye.
Bye, sir. Bye, sir. Thank you, sir.
There is an
Good night,
announcement.
everyone.
There is an announcement. Tomorrow the session will start at 2 o'clock. So be present. Tomorrow is the last date, and evening there will be test at 6:30. Okay, 6:30 to 7:30. You have to take the test by going to your portal. Okay, by going to your ATAL portal with your mail ID and password. You have to give the test. Okay, thank you. I hope you will join at 2 o'clock tomorrow. Good. Thank you.
Thank
We'll
you,
stop the
sir.
session.
Thank you, sir. Thank you, sir. Sir. We'll end the session, sir. Okay.
Okay.